Hello, my fine fiends. I'm going to do just a couple. This video is going to be pretty short. I'm just going to do a couple of problems, a couple of the exercises in section 1.8. Yeah, I think they're kind of interesting, so I want to go through them with you a little bit. I'm going to shut up my video, and then I'm going to show you the problems. Here we go. There's my screen, and here we go. These are the some exercises in 1.8, and I want to do the one, let's see, I wanted to do number 3 and number 4 right now. I want to do number 3 and number 4. They're kind of interesting, and I want to do them now. So let's go right to, here we go. 1.8, number 3. This, by the way, this is the Google Doc, which I gave you the link to. So if you ever want to just look directly on the Google Doc, it's all right there. Anyway, prove the sum of two odd squares cannot be a square. So it's a couple of things. One is that every integer is either of the form 4k, 4k plus 1, 4k plus 2, or 4k plus 3. In other words, if an integer is divisible by 4, it's of the form 4k. If an integer has a remainder of 1 when you divide it by 4, then the integer is of the form 4k plus 1. For example, the number 21 is 4 times 5 plus 1, so k equals 5. The number 30 would be 4 times, k equals 7, 4 times 7 plus 2. The number, for example, the number, I don't know what the beep is. The number 31 would be also 4 times 7 plus 3. So that's the story. Because every number is either divisible by 4, has a remainder of 1, has a remainder of 2, or has a remainder of 3. Now, what happens when you these are all numbers, every integer is one of these 4. So let's see what happens when you square these 4 different guys. What happens? So when you square 4k, you get, now I kind of rewrote this in a way that's convenient for me. You get 4 times 4k squared. Now, why did I write it this weird way? Because I want, well, you'll see my point. When you square 4k plus 1 squared, you get 4 times 4k squared plus k plus 1 at the end. Now, again, I'm writing this in a kind of weird way, but I have bizarre reasons for it. And here I have, when I square 4k plus 2 and I square that, I get 4 times 4k squared plus 4 plus 1. When I square this, I get 4 times this blob plus 1. But you see on this list here, when every square is either going to be a multiple of 4, like this is a multiple of 4 because it's 4 times something. This guy down here is a multiple of 4 because it's 4 times something. And the other two, which are not multiples of 4, they have a remainder of 1 when you divide by 4. So they're of the general 4k plus 1 form. Now that is important. That is important. So that's what we see from this list here. Well, now all this is a preamble to doing the actual problem. We want to take the sum of 2 odd squares. Well, if you take, so an odd number, so 2a plus 1, that's an odd number because it's 2 times something plus 1. It's an even number plus 1. 2b plus 1, that's another odd number. So I'm squaring 2a plus 1. I'm squaring 2b plus 1. I'm combining them all. I get 4 times this whole mess here. Again, you just combine and rearrange everything. Plus 2 at the end. Notice that this number here is of the general form, the general 4k plus 2 form, meaning this has a remainder of 2 when you divide it by 4. But we saw in the list above, we saw that no perfect square has a remainder of 2 when you divide by 4. Every perfect square is either going to be a multiple of 4 or it's going to have a remainder of 1. The fact that when I add 2 odd squares, I get a number which has a remainder of 2, that shows from our argument, from our original argument, that's why I did this whole original thing, that shows that it cannot be a perfect square. And that's the story, that's the argument, that's the proof. Yay. Okay, next one. Now this one seems like a harder problem, but it's gonna in a way be quicker. Well, if you do it this way, there are different ways how to do this. I just want to fix this so it's all on the same page. There are different ways you could work this problem. I'm just showing you one of many ways to solve this problem. So you want to prove that the cube of any integer is the difference of the squares of two integers. So if you take any perfect cube, that will be equal to some number some number squared minus some other number squared. Already. And let's do it. Well, one thing we notice, so I'm going to show you something very slick. One thing we notice here is that if I take n cubed, so this is a cube of an integer, well, that's equal to 1 cubed plus 2 cubed plus dot 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 plus n cubed minus 1 cubed plus 2 cubed plus dot 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 plus n plus 1 cubed. We'll put a little plus there. Plus there. Alrighty. But we know that 1 cube plus 2 cube plus dot 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 plus n cube, we know there's a formula for that. That was one of the exercises in the end of section 1.1. There's a formula for the sum of the cubes of the first n digit numbers, n positive integers, and that is n times n plus 1 over 2 squared. So this sum, this here of n cubed, the sum of the n cubed numbers, the first n cubed numbers, is equal to n times n plus 1 over 2 squared. This here is n minus 1 numbers, so I'm sort of putting in n minus 1 into the formula, and so I get n times n minus 1 over 2 squared. Well, I'm done, because I have a cube. It's equal to this thing squared minus that thing squared. So I've really shown, I'm done. I've taken any cube, n cubed, n is any integer, and I've shown that it is the difference of the squares of two integers. Yay for me. Now, I don't know if you want to call this an alternate proof. You could either call this checking the answer, or you could call it an alternate proof if you want. Either way, it doesn't matter. But if I would suppose I start with this final result here, just to show that this truly is an identity. In order to get this whole, whatever, let's say I start from here. Well, so I say n cubed is equal to n times n plus 1 over 2 squared minus n times n minus 1 over 2 squared. And now I want to verify this. Well, if I multiply this out and multiply that out, I could factor out an n squared, because that n gets squared and that n over there gets squared. And then I can factor out the over 4. That's why the 2 squared, I put it at the end of everything. And then inside I have n squared plus 2n plus 1, which is n plus 1 squared, minus n squared minus 2n plus 1, which is n minus 1 squared. And now when I just combine this, a whole bunch of stuff cancels, and I get n squared times 4n over 4, because the n squared minus n squared disappears, the 1 minus 1 disappears, but 2n minus negative 2n, that becomes 4n. So, but n squared times 4n over 4, if I just cancel out the 4s, that winds up being n squared times n, which is n cubed. So this kind of just verifies that it works. I guess, really you really could have theoretically just done this part right here. The only thing is, how did I ever know to do this? I figured it out based on this little formula, this little whatever. Anyway, I'm just kind of showing you my process. Well, these are ways of doing two of those problems. Hope you enjoyed it, and that is the end of this video, and we will see you next time. Bye, everybody. Bye.